All right. Hey, everyone. It's me, Aiden. I'm back. I'd like to make a video today talking about the relationship between potentials and fields and things like that, and then also how that relates to voltages and circuits. And we'll talk about some simple circuits. So I'll start sharing my screen, and then here we go. Okay. So what you can see here is I've got a potential, right? So I've got a +2 charge on the left right here. And then on the right, I've got a -1 charge. And so I wanted to introduce you guys to a pretty common sort of conception of what these charges and like fields and stuff sort of look like. And that's that the positive charges are these big bumps and these negative charges are negative bumps, like they're little holes. So if I take a positive charge and I put it on here, I can tell where it's going to go by where it would roll like a ball, right? So it's going to roll like a ball, sort of. If I put a ball right here, it's going to roll down and into this, right? So that's the idea behind potential, right? Potential is, the reason I chose to put it on this graph is because it is a function of x and y. And it is the height above the graph at point xy. And the graph is determined by the formula that we've seen before, k, oh man. Let me undo that real quick. All right, so the graph we've seen before is, we've seen the equation before, so it's k q over r is the formula for this. And when we're solving for this, what we'll notice is the values are summed. So if I put, let's say I put two positive charges, one right here, plus, and one right here, plus, at a distance r away from each other, right? I could go through all the trouble of finding the algebra of these two, right? If I want to find the field at this central point, I could go through all the trouble of trying to find the algebra of both of these, but I could also think about it this way. I could draw my little field, right? I have my potential right there. My potential for this one is over here. And then they have their little yellow feet of their mountain. And then where I'm trying to find is actually this mountain pass. So it's right here. Right here is much higher than the surrounding area, right? So this is the surrounding area. I'll keep drawing out my diagram here. And then we get, and I'll use green for just the general backdrop, right? So what we see is this is sort of this mountain arising from the general green backdrop. And if we're trying to find this potential right here, that's what we're trying to find, right? So I'm trying to find what is the value of the potential here. Well, if you look, it's the field of this one and the field of this one sort of added right here. So I'm going to get a superposed field that looks sort of like, and I'm going to erase some right here real quick. So it looks sort of like, I'll go back to my marker and change to the pen, and then we get something sort of like this for a shape, maybe, roughly. So we've got this, and this is our values. And what it is it's KQ1 over R1 plus KQ2 over R2. And the magnitude of the charge is what determines the value of this, but the sign of the charge actually tells me whether these are going to be added or subtracted. Notice right here on these, I marked these equipotential lines over here with black. There's one right here, and one right here, and then one over here, and then some going down into here. These are equipotential lines. And the equipotential line for zero potential right here, right, I'm going to mark that pretty good and erase around it. That line lies where the potentials for both of them are 0. Um, let's clean this up some. So this line lies right here where the potentials are 0. You'll see me moving my pen over it. And it's a really important point because we can say right there that KQ1 over R plus KQ2 over R is 0 just by looking at this graph. So this graphic representation is a really super powerful tool that we have for working with electromagnetic stuff. And now let's move on to thinking about the field for a second. So I will change to a pen again, if I can get work. Right. So the field is actually just the slope. Right. So if I take this path, let's say and I'll make my path, let's make it maroon. Right. If I take a path right here, I want to start here and I want to travel down my slope, right? And then down into this. Well, so my slope at any given point right here is going to be actually equivalent to the magnitude of my field. And what that tells me is that if you've ever taken calculus, you'll see this as sort of as a derivative along this path. If you haven't taken calculus, just think of it as the m in y equals mx plus b. If I were to draw a tangent line right here, so let's say I choose this point P right here. I draw a tangent line at P, and the tangent line has slope m, so y equals mx plus b, where x comma y is equal to p, right? So what we'll have here is if we just choose this line and we take this tangent line right here, sort of like, just picking a point and making it into a straight line, we've got this concept that it is the electric field there. That's the slope of the potential at that point. And there's some complicated vector calculus you'll see here. You'll come across the symbol probably further in your studies. It looks like this. It's called del. Del is the gradient operator. So if I take del f, it gives me the slope in a more sort of like formal way. So that's exactly what this is. But I'm going to erase all this, and then we're going to move on to thinking about how this works in a problem. And then we're going to move on from the problem to a little bit of circuits. So let me do my selection there. Okay. I got my fancy new pen here, everyone. That's why this is going a little smoother than usual. So we take this and we have, and this is a common problem that we have particle A right here, and particle B right here, and we have a point C that's sort of unmarked. I'll keep that over here, right? So, and we have distances right here, and these are at right angles. To be really clear, these are at right angles. Let me undo. We have distances at right angles here of R of A, and right here is R of B, right? And we have Q of A and Q of B, so I'll do those in yellow because electricity. So Q of A and Q of B. And so a lot of people, their first inclination is to do something like this. They'll do K, Q, Q over R, question mark, right? So they kind of like start off by trying to solve for this using the potential energy formula because potential and potential energy sound really similar and it's kind of hard to keep them separate sometimes. This is a big, big no-no. We do not want this. We do not want to use this formula here unless we have a known charge right here because we have two charges, so we're going to want to put these two charges in here, and that's wrong. So what we need to do to find the potential at point C is we need to take the potential from A, which, where's my pen? Okay, the potential from A is P, or I'll use phi. I'll use phi for my character. Phi is the most common character for potential. So using phi is pretty much standard practice. Let me, come on. All right, so we've got phi of A, comma C, plus phi of B, comma C is equal to phi just of C. So phi at C, right? So to solve that, we use K, Q, A over RA. And now here's the key, plus K, QB over RB. So we get this nice, strong relationship here. I can actually factor the K out, and we get that this is equal to K, I'll write this big over here, times QA over RA plus QB over RB. And if we want to generalize this formula to any number of charges, we want to find any number of charges acting on this point right here, where each charge, and let me clean up some space here, we'll assume that each charge has, oh no, that's not what I want. Sorry for the delay. We'll assume that, and if I fix that, each charge has the form Qn, right? So a general charge is Qn, and for particle n, and its distance from point C, we'll call that C still, right? Its distance from point C is Rn. And so what we have is, you know, my 1, my 2, my 3, my ... n particles. The potential here at C is actually equal to, so phi at C is actually equal to K times Q1 over R1, where R is the distance between them, plus Q2 over R2. Again, R is the distance between point 2 or charge 2 and C, plus Q3 over R3 ... So that's the very general way to say it. And notice that what this is telling us is just that if we have Q and R, the potential at that point, right, is just the sum of all the other potentials. So we can find the point, you know, in our original problem, we can find the potential at point C just by adding the potential from point A plus the potential from point B. Okay. This is actually also voltage. So voltage is moving, we're moving into circuits, so we can talk about voltage a little bit. But we have, you know, the direction doesn't really matter because it's a scalar. We just need this distance between each of these. That's all that this depends on. The direction isn't there. Okay, so this is the general formula right here. I'm going to make a new box, and I'm going to, in that box, I'm going to draw the general formula that we use for this, for pretty much everything. So here's my box, and this up here that I just wrote can be rewritten this way. So phi, come on. So we've got phi, oh, come on. So phi at point C is equal to K, and then this is the exact same thing with a little bit of new notation, times the sum from 1, so I is equal to 1 to n, and you'll probably see this again, of Q I over Ri. So these are equivalent. One just says the same as the other one. We really like these nice sums in physics because they are easy to deal with. thing, all it's saying is literally just a bunch of plus signs. That's what this is. But it's a succinct way to remember what you're looking for. So you're just looking for the sums of this potential, this potential, this potential, this potential. Okay. Now let's think about just for a minute. We will think about current in wires. Yay! Okay, so let's say I have a wire, and I'll model it like a pipe here, right? I'll model it like a pipe. There's my wire, and I have my electrons, and they're flowing down my wire, so they're going down the wire towards, oh no! Undo that. Yeah, towards my positive side, and I'll do that in red, and away from my negative side, right? So what drives these charges we generally call voltage, right? And we realized earlier on that voltage is equal to joules per coulomb. So what that means is if I have, and a coulomb, just to throw this in there, a coulomb is actually equal to a very large number of electrons. So it's equal to K, which is a really big number, or let's not use K. Let's use Z times the number of electrons, right? Where Z is a really large number, or sorry, times the charge on the electrons. So let's erase that. Times Q electron. All right, so a coulomb, we can think about it this way, it's just some number of electrons. It's just some number Z of electrons. It's a really large, really, really, really large number that I don't think you need to know, that might pop up on your formula sheet. And so if we take this and we run with it a little bit, what we can see is that we're given an electron here, and that electron has some potential energy across this distance, right? So that, when we're talking about current, we're talking about joules per coulomb, and then I is in units of coulombs per second. So we have a certain number of objects traveling down this way, which are electrons, and they each have a potential energy given by the voltage times the charge on that electron. And then they meet resistance by running into the objects inside the wire. So this is a pretty simplified model of what's actually kind of happening. If you want to look it up, it's called, I'll write that down, the Drude model. Drude model. And it involves, again, some vector calculus, but you don't need that. So you can keep it pretty simple. But the idea is that, and if you've taken chemistry, you'll know this, the idea is that the electrons are kind of like a gas, and they're traveling through the pipe, and they're hitting the protons. And when they hit the protons, that is actually what causes resistance. So that's why the resistance is a function of the material. And it's also why electron flow can be thought of in terms of potential energy. So it's a little more complicated than that in real life, but this is a great approximation for our purposes. Okay, so let me clear off some space and we'll go over one last thing. And so we'll talk about some basic circuits. So let's talk about, I'm trying to get, so let's talk about, we have a circuit, right? And it's got a resistor, and it's got a capacitor here, and a battery. And let's just to be fun, let's add another resistor here. So this is called an RC circuit, and it does not mean remote control. It's a very specific kind of RC circuit, but it is an RC circuit. It has resistors and capacitors. So we have a voltage V being generated by the battery, which is just the potential energy between terminal A and terminal B per charge. And the resistor uses up some amount of voltage. It uses some amount of energy. right? So that's where we get V equals IR, right? Well, the resistance of this entire system is actually equal to the resistance of each component. So this implies that V is equal to I times the sum of the resistances. And I'm going to use big sigma for my sum here again. So just so you guys can get kind of used to it. So it's used, and I'll use I just to say that it's over the indices. So we have indice 1, this is I equals 1, this is I equals 2. So we have V equals I times the sum of the resistances. That's in series. So this is a series circuit. We say series. Let me erase some of this so that I don't have to confuse it. So this is okay, so here's a series circuit. I got my voltage, my 2 resistors. It's this way. Now, that's because the electrons traveling through here, they go through and, oh no, this resistor eats up some of my electrons. It eats up some of my energy that my electrons had, right? So then it's going. And then, oh no, it eats up some of the energy that my electrons had here, and then it's going, and it makes it back to its terminal. Now, what this tells us is that the current has to be basically the same everywhere, right? So we get a voltage drop from this resistor, we get a voltage drop from this resistor, but the current is constant. The reason that the current is constant is because we don't detect some really big buildup of electrons here, and then some, like less electrons over here. And then the same thing here. What we detect or what we see is that the electrons flow relatively smoothly, and there's no big bunch ups, right? So any big bunch ups we see would end up acting sort of like, I almost want to say like a bundle of charges, and we don't see that, so we end up only looking for a constant current. So the current is constant. In this case, we don't have an alternating circuit. We may also see some current changes with inductors. I'm not going to get into that yet. Current is constant here in a series resistance circuit, okay? And then we're going to erase a little bit of this, and we're going to talk about, since the current is constant, okay. Since my current is constant, so I equals, let's just call it big K or little k for our purposes, or kappa, right? So I is equal to kappa. So V for this circuit is equal to kappa R. So that means, and then V is also equal to kappa times the sum, like we said in the last part, of the resistances. So what that tells us is that as we patch each resistor, we actually drop some of our voltage, right? So we drop some voltage here, so minus some fraction of V, and then right here we have some fraction of V and some fraction of V, and that fraction is actually just that ith term times kappa. So what we get is that delta V is equal to I delta R. Wow, that's pretty painless. That's a nice, easy formula to remember. So I'm going to make that nice to remember by making it an orange. That's good. That's easy. This is a nice, easy system to work